I hope you all are having a good Friday. I'm going to look at a couple of web work problems, one from homework set number 2 and another one from homework set number 3, because I've received a few emails about them, and so I figured it might be useful for me to kind of address those problems with the class as a whole. And it'll reinforce some of the things that we have learned to this point. So let's look at homework 2, problem 4 first. So in this particular circuit, we have a current source. It's given with direction down, and my value is a positive number, so I'm going to leave it direction down. So it'll be 6 amps. That may be different for you guys, but the process will be roughly the same. In parallel with that current source, we have a 20 ohm resistor through which a current IX flows. And the voltage Vx is defined as the voltage drop across the 20 ohm resistor with the positive polarity terminal on bottom. In parallel, we have an additional resistor. So this is a 12 ohm resistor. Through which a current of IY flows. In parallel, we have a current source I2, direction up. My value is positive, so I'm going to leave it as a direction up current source, 2 amps for me. And then lastly, over here on the right, we have a dependent current source with a value of 0.25 Vx. We're also told that we have a current IZ flowing down through that branch. Okay. So our ultimate goal in this problem is to solve for the 3 labeled currents, IX, IY, and IZ, and we're going to wind up solving for that voltage Vx as an intermediate step. So I believe I've mentioned before, but anytime that we have a circuit where everything is connected in parallel, one of the best things for us to do is to apply Kirchhoff's current law. I'm going to apply KCL, the formulation where all of the currents exiting the top node, which I believe we're calling KCL number 2. So all of the currents that are leaving the top node are going to be positive. And so if I apply KCL here, just going from left to right, I'm going to have 6 amps plus IX plus IY minus 2 amps. And here I have a choice. For this rightmost branch, I can either choose to represent this current as IZ, or I can choose to represent it as negative 0.25 Vx. And the reason why it's a negative sign there is because the current is flowing into the node, and I am adopting a convention that currents flowing out of the node are positive. So I know that ultimately I'm going to wind up having to write an equation only in terms of Vx. So I'm going to go ahead and introduce Vx into this equation. So I'm going to choose to express that rightmost current as 0.25 Vx, like so. And I'm going to set this equal to 0. So there's my first equation. Now I'm going to use Ohm's law in order to express IX and IY in terms of my voltage Vx. So let's do that here really quickly. So I can say that Ix is going to be equal to negative Vx over 20 ohms. The negative sign comes from the fact that the current is flowing into the negative polarity terminal. Similarly, I can say that Iy is negative Vx over 12 ohms. And I'm going to substitute those two relationships into my KCL equation. So what that's going to do is give me the following relationship. Sorry for all of the arrows all over the damn place, but I'm going to have negative Vx over 20 ohms minus Vx over 12 ohms minus 0.25. Just for the sake of argument here, what should the units be on that 0.25 scaling coefficient? Anybody remember from our second lecture? So this is a voltage controlled current source, because it's definitely a current source because there's an arrow, and it's voltage controlled because it depends on the voltage Vx. So that means that 0.25 has to have units of amps per volt. So I'm going to go ahead and just put that in parentheses here. Amps per volt, which is the same thing as 1 over an ohm times Vx, so that the units all work out effectively. And over here on the right-hand side, I'm going to add 2 amps and subtract 6 amps. So that's going to look like negative 4 amps. And now I have a single equation with a single unknown quantity, Vx. So I can use the numerical solver in my calculator or some other method if you guys choose to do that in order to solve for Vx. So give me just a moment to throw this in my calculator. So negative x over 20 minus x over 12 minus 0.25, x is equal to negative 4. I'm just going to guess the value is 1. My calculator is now trying to solve. So I got positive 10.4347, so let's call it 435 volts, assuming I typed everything in my calculator correct. I believe the process is right. So from here, we know that Ix is simply negative Vx over 20 ohms. So negative x over 20 comes out to be negative 12 over 23 amps, or negative 0.522. Iy is negative Vx over 12 ohms, or negative 20 over 23 amps. In decimal form, that looks like negative 0.870. And lastly, we know that Iz is equal to negative 0.25 Vx, or negative 2.609 amperes. So that's how I would solve that particular homework problem. Before we move along to the next problem that I get a lot of questions about, does anybody have any questions about any part of my analysis? I just want to make sure I don't accidentally have you guys muted. Nope. Okay. My volume's on, so just nobody's talking. All right, that's fine. So now we're going to look at homework set number 3, problem 1, which I very regularly get questions about. Um, so I'm going to go ahead and draw the circuit as it is drawn on WebWork, and it is drawn in a way to be, I believe, intentionally confusing. And so our first big step in this particular problem is going to be to redraw the circuit in such a way that it's more akin to what we're used to. Okay. So we have this very gross looking circuit. We have a resistance R1 where my value for R1 is 12 ohms. Then we have a resistance R2. My value is 98 ohms. We then have an independent current source direction to the left, whose value is 4.5 amps. Then we have a resistance R3, so that's 55 ohms for me. And then we have a dependent current source direction to the right, whose value is 0.5 Vx. And then lastly, over here on the right, we have resistance R4, which is 114 ohms. Then we have all these weird kind of loops and swoops. So let me attempt to draw them really quickly. So there is a loop here, another one here, another here. Sorry about that. And then we have 2 on the bottom, like so. Our current I1 is defined as flowing through this top kind of loop thing. Here's I3, here's I5, here's I2, here's I4, and we also have a voltage Vx defined to be the voltage drop across the resistance R2. So I'm going to do something here really quickly, and I'm just going to identify nodes. So all of that is one large node, which I'm simply going to call the top node. And then all of this is one large node, which I am simply going to call the bottom node. So if I were to redraw this, I would start by just labeling a top node on top and a bottom node on bottom, like so, and then making connections, right? So between the top and bottom nodes, we have that 12 ohm resistor. So let's put it right here. Between the top and bottom node, we have a 98 ohm resistor. Between the top and bottom node, we have that independent current source. And the current is flowing from the bottom node to the top node. So I'm going to put the arrow like this. Between the top and bottom nodes, we have the 55 ohm resistance. Between the top and bottom nodes, we have that dependent source, where the current is flowing from the top node to the bottom node. So that's why I drove the arrow in that particular direction. And then lastly, over here on the right, we have our 114 ohm resistance. And now I'm just going to connect all this together on the top. Connect all this together on the bottom. The voltage Vx is defined with the positive polarity on the top node and the negative polarity on the bottom node. So this is just as good of a location as for Vx as anything else. And then the hard part here is actually figuring out where to put these currents I1, 2, 3, 4, and 5 in this new drawing. So let's look at some things really quickly. Okay. So the current I1 is originating from this point where the one of the terminals of the 98 ohm resistor is connected to the 4.5 amp current source, and it's connected to the node that the head of the arrow of the current source is connected to. So that's effectively this node right here. And it's flowing through the 12 ohm resistor on its path to the bottom node. So I would say that this represents my current I1. My current I3 is originating at this point in our circuit, which is where the 55 ohm resistor and the tail of the 0.5 Vx current source are connected together, which would be this node right here. And it's flowing to the node where I1 started from. So I'm going to call this current right here I3. The current I5 is flowing from the bottom node to the top node through the 114 ohm resistor. So I'm going to draw it right here. Let's see. The current I2 is originating at the node where the tail of the 4.5 amp current source and the 55 ohm resistor are connected together. So that would be right here. It's flowing to where the 12 ohm resistor and the 98 ohm resistor are connected on the bottom node, which would be right here. So that means this current is I2. And then let's see. Lastly, we've got the current I4. It's flowing from where the head of the 0.5 Vx arrow is in the 114 ohm resistor, so right here. And it's flowing to what I circled as the orange node. So this would be the current I4. Does anybody have any questions about how I redrew this circuit before we move along to the analysis?
No, sir.
Alrighty. So what I'm going to do now is I'm going to write a Kirchhoff's current law equation at the top node. And let me do something here really quickly. So effectively, I'm going to be adding all of these currents that I'm about to outline in gray together. And whenever possible, I'm going to express those currents in terms of the voltage Vx that's common to all of these elements. Okay, so KCL number 2, the currents that are exiting the top node, to me, the current that's flowing down through the 12 ohm resistor could be expressed as Vx over 12 ohms, just using Ohm's law. Very similarly, the current flowing down through the 98 ohm resistor would be Vx over 98 ohms. Then we would have minus 4.5 amps plus Vx over 55 ohms plus 0.5 Vx and then plus Vx over 114 ohms is equal to 0. And we can see right from the jump that we have a single equation with a single unknown, which would allow us to solve for that unknown voltage Vx. That is the most powerful and important piece of information for a circuit where everything is connected in parallel because it's common to everything. So once we have Vx, we're in really, really good shape. I'm not going to bother actually solving for Vx, but we can see here that we have one equation with one unknown. So we should be able to solve for that voltage Vx very easily. So under the assumption that we use this relationship to solve for Vx, now let's figure out how to determine all of those currents, I1 through I5, that you're actually asked about in the homework problem, right? So for I1, it's pretty straightforward. So let me write here, determining I1, okay? We're going to do that just by using Ohm's law, okay? The voltage drop across the 12 ohm resistor is Vx. The resistance value is obviously 12 ohms. So using Ohm's law, I1 is nothing more than Vx over 12 ohms. We can do something similar to determine I5. So I5 is the current that's flowing from the bottom node to the top node through the 114 ohm resistor. So because it's flowing in the opposite direction as the current I1 was, or because it's flowing into the negative polarity terminal of the 114 ohm resistor, we're going to say that I5 is just negative Vx over 114 ohms. These are the two that are easy. Um, all of the rest are going to be a bit more difficult. Okay, so let's look at I2 first. I'm going to use a different color here. So what we're going to be doing is we're going to effectively be applying KCL at that light blue node. We have a current of I2 flowing in, and then we have this current flowing in and this current flowing in, and they all have to add together to be 0. We could change this ever so slightly by saying that this current I2 flowing in has to equal to these two currents flowing out. which will let us not have to algebraically rearrange things. So say KCL number 3 at light blue is going to look like I2. And then how could we express the current flowing up through the 98 ohm resistor in terms of Vx? Anybody have any thoughts? We're looking at this current right here that I just circled. All right. Well, I believe that we can just use Ohm's law because we're just expressing a current in terms of voltage and resistance. Okay. So the voltage drop across the 98 ohm resistor is Vx. And so we're going to have Vx over 98 ohms. And because the current is flowing into the negative polarity terminal, we put a negative sign. For the current that's flowing up through the 12 ohm resistor, we're going to do the exact same thing. So we're going to have Vx over 12 ohms. And because the current is flowing into the negative polarity terminal, we put a negative sign, and there we go. That's how we can solve for the current I2. We can do something incredibly similar for I4. So what we're going to do is we're going to apply Kirchhoff's current law at the light purple node. So we could say that the current flowing out, which is I4, is equal to the currents that are flowing in. Oops. Sorry, KCL number 3 at light purple is going to look like I4, so that's the current flowing out. The current flowing in from the dependent source is literally just 0.5 Vx. And the current flowing in to the light purple node through the 114 ohm resistor is just going to be Vx divided by 114 ohms from Ohm's law. So we've got I1, I2, I4, and I5 taken care of. So the last one that we have to worry about is I3. So for I3, we have some choices. So we can say that the current I3 is flowing into that green node, and then this current, and this current are flowing out of the green node. Or we could do KCL at the pink node and say that I3 is the current that's flowing out. So this current, and this current are all flowing in. So I3 must be equal to the sum of those three currents. So we can either do KCL at the green or KCL at the pink. Either way is going to give us the exact same result. I'm going to choose to do KCL at the green node. So that's going to look like I3 is equal to, so the current flowing down through the 4.5 amp source is negative 4.5 amps. The current flowing down through the 98 ohm resistor is Vx over 98 ohms. And lastly, the current flowing down through the 12 ohm resistor is just Vx over 12 ohms. And now we have an equation to solve for all of the different currents that we were looking for. So to me, the absolute hardest part of this problem is redrawing the circuit in a way that makes sense. So hopefully, once we got that part figured out, all of the rest of the analysis was fairly straightforward. Are there any other homework questions or anything that you guys would like answered before we move on to today's lecture topics?
Yeah, I don't want to cut into any of your time, but could you go over homework 3, problem 3 real quick?
Let's look at it. Ian, which particular part of the problem would you like me to look at?
Starting it.
Okay,
Yeah.
so starting it, let me put this down here. So homework number 3.3. All right. So we are given a network of conductances. Okay. So I'm going to draw said network really quickly. So we've got a terminal here. Then we have a conductance. I'm just going to call this conductance G2. I'm just going to use the exact same terminology that's used on WebWork. Here is the conductance G3. I have a short circuit here. Here is a conductance G1. Here is a conductance G4. Ian, would you mind remuting yourself? There's a lot of background noise coming from you.
Sorry about that.
Here I have a switch. Across the outside over here, I have a conductance G5. And then lastly, I have a terminal over here. So this is the circuit that we are given, and we're given values for all 5 of those conductances. Now, combining conductances is a little bit of a pain in the butt, and we didn't really learn about it. But our goal here is to actually find the equivalent resistance under these different conditions. And resistances are stuff that we've been working with for quite some time, and we had a full lecture about how to combine them the other day. So if you recall from our very first, excuse me, not our very first lecture, our second lecture, when we were discussing, oh, nope, I guess it would have been the third lecture. I apologize for that. When we were discussing Ohm's law, we learned that conductances are nothing more than the reciprocal of a resistance. So we could replace every conductance in our circuit by simply doing 1 over the conductance to give us some resistance value, right? So we could replace G2 with a resistance R1. We could replace G3 with a resistance R3. Short circuit here. We could replace, sorry, I said G2 with a resistance R1. That should be R2, my apologies. This is going to be R1. Here's R4. Our switch is still a switch. Here's a resistance R5. Here's a terminal. And I'm just going to put a note up here. R is just 1 over G for all of these cases. Okay? So at this point, it's just a resistor combination problem. So if we were looking at part A, where we are supposed to treat our switch as an open circuit, then the resistance combination problem that we are trying to solve is this one. So with my switch replaced by an open circuit, I'm just not going to draw the switch at all. So I could quite easily identify my nodes. So let's call this node A. Let's call this node B. We can call this node C. And lastly, this guy over here, node D. And using the techniques that we talked about in our last class meeting, I'm trying to find the resistance between nodes A and C. So I'll put A over here and C over here. To go from A to C, I hopefully very obviously have to go through node B. So let's throw node B smack here in the middle. To go from A to B, I can go through either resistor R2 or resistor R3. So I'll put R2 on top. R3 like so. So I've got this guy taken care of and this guy taken care of. To go from B to C would go through resistor R1. I also have the path from A to D to C. So I'm going to put D down here. To go from A to D is through resistor R5. And to go from D to C is through resistor R4. And so hopefully then I could very easily see that these two resistors are in series. These two resistors are in parallel, and it's just going to be this bottom thing that I circled in green in parallel with the top path. And you could do something very similar for the other two parts of the problem. Was that helpful, Ian?
Yes, that was very helpful. Thank you.
All right. Any other questions before we move on to today's lecture topic? All right. So we have kind of four small topics to go over today. So the first topic that I want to talk about is voltage source combination. And so this is just addressing what happens when we see multiple voltage sources connected together and how we can combine them into equivalent voltage sources. So we're going to start with voltage sources in series. So whether or not you realize it, you've probably been dealing with connecting voltage sources in series for a large portion of your life, because anytime you have replaced the batteries in a remote control or something like that, or a flashlight or whatever, you have been connecting voltage sources in series. Okay. So let's look at a very simple circuit here where I have, let's just say, some generic voltage source VS1, a resistance R, across which I will have a voltage drop VR. Let's put another voltage source here. So let's call this guy VS2. And then lastly, a voltage source over here, which I will call VS3. Okay. What we're about to learn can be applied to any number of voltage sources in series, but 3 will tell us everything that we need to know. So if we were to apply Kirchhoff's voltage law to this circuit, where I'm going to arbitrarily choose this clockwise direction, we would get negative VS1 plus VR minus VS2 plus VS3 is equal to 0. And we could rearrange this in terms, so we would put the voltage drop across the resistor on one side of the equation and all of our source voltages on the other side of the equation. So think about it in the context of we are seeing the equivalent voltage that the resistor sees presented by this combination of different voltage sources, okay? So simple rearrangement says that VR is going to be VS1 plus VS2 minus VS3 is equal to some equivalent voltage source. Okay. So let's see if we can glean some information about what's going on here. Okay. So I believe that the polarity of the voltage source VS1 and the polarity of the voltage source VS2 are the same. And I am saying that because when we went around our Kirchhoff's voltage law loop, we saw the negative polarity terminal for both of those voltage sources first. VS3 is of the opposite polarity because we saw its positive polarity terminal first. So what it looks like is that voltage sources that have the same polarity just get added together, and voltage sources that have the opposite polarity get subtracted from the total. And that's really how we combine voltage sources in series. So think about this in the context of changing the batteries in a flashlight or something like that, okay? Let me draw a very simple circuit down here. So let's say that we had one battery, then another battery. And let's make this a 1.5 volt battery, like a double A battery. Here's another 1.5 volt battery. Up top here, we have a simple switch. And then this is the schematic symbol for a bulb. And we can think of an incandescent bulb as literally just a resistor. Its job is to heat up and emit light. Okay. So when that switch is closed, how much voltage is applied across the bulb?
None.
I disagree.
Oh. Is
So
it negative 1.5?
there's only two 1.5 volt batteries. So the only possible options are +3, -3, or 0. And I told you explicitly it isn't 0. Right. So KVL tells us the answer, right? So if this is the voltage drop across the bulb, we would have -1.5 volts minus 1.5 volts plus V bulb is equal to 0. Rearranging, V bulb is 3 volts. Does that make sense?
Yep, it's good.
Okay. So what if I accidentally put one of the batteries in backwards? What would change?
Would it then just be 0 volts?
Exactly right. So this sign would change to positive. So positive 1.5 minus 1.5, or 0, plus V bulb is equal to 0 means that our bulb receives no voltage. So if we accidentally put a battery in backwards, the flashlight isn't going to work. That's probably something that you guys have experienced on accident before, right? You're not paying attention, you're putting the batteries in, accidentally get one of them backwards, and whatever you're trying to make work doesn't work. Well, it's because the device is no longer receiving the correct amount of voltage to make it work. In a simple case like this, where it's exactly 2 batteries, it cancels out completely. But you guys used a battery pack in your Engineering 120 series, where you had 6 AA batteries in series, so a total of 9 volts. And if you put one in backwards, you were only going to get effectively 6 volts out of the battery pack, which might not be enough to actually power your Arduino. So anyway, I believe that combining voltage sources in series is fairly straightforward. It follows a very simple rule. Like I said, if the polarities are the same, you add them together. If you have a voltage of the opposite polarity, you just subtract it. Any questions before we move along to voltage sources in parallel? All right. So voltage sources in series, as I mentioned, is something that we are all likely familiar with, because that's effectively what we're doing when we're changing batteries and all of that kind of good stuff. Voltage sources in parallel is something that's done a whole heck of a lot, but the reason behind why it's done is not remotely intuitively obvious. So we're going to talk about it here a little bit. Okay. So voltage sources are connected in parallel in applications that are dealing with effectively energy storage and things like that. So if you have solar panels on your home, or your parents have solar panels on their home, there is a very distinct possibility that some of the solar panels are connected in series, and other parts of those series connected banks are connected in parallel. And the reason why you would do this is to make sure that the voltage is the same across all of the parallel connected banks. However, the total amount of current or power that can be output is much larger than what could be handled with all of them connected just in series. Okay. I do some work for a company called Sabre Industries, located out of Bossier City, Louisiana, and I design usually just the bus work and stuff like that that goes into their battery energy storage containers. And in these battery energy storage containers, we have racks full of lithium ion batteries, where we have a whole bunch of cells connected in series to get us to a voltage of about 1500 volts. And then we connect up to 50 of those battery racks in parallel in order to push out thousands of amps of current, so that we have a large module that's capable of supplying up to a megawatt of power to a local utility grid. These are typically tied to solar installations and all of that kind of stuff. I'm mentioning this just to say that connecting voltage sources in parallel happens a lot more often than you would think it does. So I just wanted to bring that up. So now let's look at voltage sources in parallel from a circuit analysis aspect, and things can go a little wonky here. Okay. So let's say that I have a 5-volt source. And then over here, I have a 10 ohm resistor. And over here, I have a 5-volt source. So I'm going to ask you guys what I hope are some fairly obvious questions, but it's okay if you're a little confused or anything. What is the voltage drop across this 10 ohm resistor?
Five volts.
5 volts, absolutely right. What's the current flowing through the 10 ohm resistor?
0.5 amp.
Absolutely right. So we should be able to surmise that exactly half of that current, so a fourth of an amp, is going to come from the 5-volt source on the left, and a fourth of an amp is going to come from the 5-volt source on the right. So the reason why we might connect voltage sources in parallel is to either spread the burden of supplying current across multiple voltage sources, or to boost the current to higher levels than could normally be achieved by a single voltage source. Okay. So this is an example of voltage sources connected in parallel where everything works out nice and neat. Okay. So this is going to get a check mark because everything seems okay. Now I'm going to break things. So I'm going to draw almost the exact same circuit. So here's a 5-volt source. Here's my 10 ohm resistor. But now on this side, instead of having another 5-volt source, I'm going to put a 3-volt source. What's the voltage drop across the resistor?
Eight volts.
8 volts. Okay, incorrect.
4.
Incorrect. One more guess.
Is it 5 volts?
Also incorrect.
2.
The correct answer is there's no way to know. So let me explain what I mean by that specifically. This was a trick question. I'm being a little bit of a jerk. The short answer here is that we cannot use circuit analysis to analyze this particular network, and I'll explain why in just a moment. If we were to write a KVL equation around this left-hand loop, we would see, I hope very easily, that VR is equal to 5 volts. If instead we wrote a KVL equation around this right-hand loop, we would see that VR is equal to 3 volts. If we wrote a KVL equation around the outside, we would see that 5 volts is equal to 3 volts. That literally can't happen, right? So whenever we have voltage sources that are connected in parallel and the voltage sources are unequal, we have to stop. There's literally no amount of circuit analysis that we can do because we are effectively violating one of our fundamental laws of circuit analysis that says the sum of the voltage drops around the closed path has to equal 0. Now, could I physically make a circuit like this, where I put 5 volts in parallel with a 10 ohm resistor in parallel with a 3 volt source? Absolutely. What would happen is that the resistance of the wires would effectively be trying to take up that imbalance. So realistically, a very, very large amount of current, probably about as much as the battery could possibly supply, would wind up flowing through this section of wire right here and make that 3 volt battery incredibly hot because it's effectively trying to be charged up by that 5 volt battery, and there's not a lot of resistance to limit the amount of current that's flowing into it. Okay. Way back in the day, so this would have been probably 5 or 6 years ago in the Engineering 120 series, the battery packs that you guys were given just had loose wires. And it was several weeks into the class that the barrel jack was soldered on. And so we had to tell the students after leaving class every single time, hey, make sure you take the batteries out of your battery pack, because we would just have them connect the wires directly to the breadboard to power things up. We had to say, hey, make sure you take the batteries out of your battery pack, because if you accidentally cross those wires, the battery pack would heat up enough that it would melt your little bag that your kit came in. Very, very dangerous. So that's why we stopped doing that a couple of years back. So anyway. All right, so we've talked now about combining voltage sources in series, which is fairly straightforward. Voltage sources in parallel, we have to pay a lot of attention to. We are not going to see voltage sources in parallel a lot in this class, but I did want to bring them up because it is something that you see practically, and it reminds us that the circuit analysis that we're doing in this class is on ideal systems where wires have no resistance, this, that, and the other. In a real case, those wires actually do things. All right, any questions about combining voltage sources before we move on to current sources? All righty. So to start off our discussion on combining current sources, we're first going to look at current sources in parallel. So let's say that I have a 3 amp current source direction up connected in parallel to a 1 amp current source direction down, connected in parallel to some resistance R. Sorry, let me get rid of these numbers. We'll do it symbolically like we did for the first resistor example. I apologize for that. So let's call this IS1. Let's call this IS2. This will be R. This is the current IR. And lastly, over here on the right, let's have another current source up, where this will be IS3. Sorry for changing my mind midstream there. So if we were to apply KCL number 1 at the top node, what we would have is IS1 minus IS2 minus IR plus IS3 is equal to 0. Our goal here is to see what equivalent resistance equivalent current source the resistor is going to see. So I'm going to put the IR term by itself on one side. And that's going to leave me with a combination of IS1 minus IS2 plus IS3 is our equivalent current source. So we're seeing something here that's very similar to what we saw with our voltage sources. Whenever our current sources have the same direction, like IS1 and IS3, they add together. And whenever our current source is in the opposite direction, it gets subtracted from the equivalent current source. Okay, so very, very similar to what we saw when we were dealing with voltage sources in parallel. Excuse me, voltage sources in series. I apologize for that mistake. So just to work a quick numerical example. Let's say that I have 3 amps, 1 amps, an 8 ohm resistor, and two amp source like so. And I want to figure out what the voltage drop across my 8 ohm resistor is. I could apply KCL like we've been doing and wind up actually applying KCL and Ohm's law, or I could combine these current sources into a single equivalent current source, which would be connected in parallel to my 8 ohm resistor, like so. So because I've drawn my equivalent current source with a direction up, all of my current sources with direction up are going to be considered positive, and all of my current sources with direction down are going to be considered negative. So what do you guys think the equivalent current source should be?
4 amps.
4 amps, absolutely right. 3 minus 1 plus 2 is equal to 4 amps. And so from that, V8 is 32 volts. It doesn't need to be literally any harder than that to combine current sources in parallel. And this is definitely a technique that you can use on some of your homework problems. Sorry, let me look at really quickly here. So if we looked at homework set, I believe number 4. Homework set number 4, problem 1. could be used. Also, problem 5 would be a very good application of combining current sources in parallel to make the circuit significantly easier to analyze. Okay, so now let's look at current sources in series. So we're going to start with a system where everything works out okay. So let's say that I have a 2 amp current source, a 10 ohm resistor, and then another 2 amp current source. And I want to know the current flowing through the resistor. I hope that it is very obvious that the current is 2 amps. According to Kirchhoff's current law, if 2 amps is flowing into this node, then 2 amps has to be flowing through the resistor in this direction. Applying KCL over here, if 2 amps is flowing out of this node, then 2 amps must have been flowing in. So either way we look at it, the current flowing through the resistor is 2 amps. Everything works out okay. So this is perfectly fine. So whenever we have those two current sources in series, as long as they have the same magnitude and direction, everything works out great. Instead, let's look at this. So 2 amps, 10 ohm resistor, and now we have a 1 amp source, right? So if we were to apply KCL right here, I'm going to define my resistor current like so, we would be able to say that, I'm sorry, let me do it in red. IR is equal to 2 amps. If we applied KCL at this blue node, we would have IR is equal to 1 amp. And if we applied KCL at this green node, we would have, 1 amp is equal to 2 amps, which obviously does not work. So if we ever see current sources that are connected in series and they don't have the same magnitude and direction, we have to stop what we're doing and just walk away because we're violating the laws of physics again. Now, in a practical case, the only place that you would ever see two current sources connected in series would be transistor related circuits where you're using current sources to bias more complicated electronic networks, and you're really just using transistors themselves to act as a current source. So in practice, because they would be part of the same path, they would wind up carrying the same amount of current, and the non-linearity of those devices would make the voltages just kind of work out in order for the currents to be the same. So you would be very hard pressed to ever find a practical situation where you had two current sources in series and they didn't carry the same current. As far as I know, it can't be done. So it's not something that you should ever really worry about. All right, we went through current source combination fairly quickly. If anybody has any questions about it, I would be more than happy to answer them. If not, we will move along to our next miniature topic for today. All right. So the next thing that I want to talk about is voltage division. Voltage division is a very handy tool for determining the voltage drop across a resistor that is part of a series connected resistor network without having to go through the steps of solving for currents and things like that. So it's just a shortcut, but it can be very, very useful, particularly on some of the homework problems, stuff like that, that you're given in this class. Now, whether you realize it or not, you have actually done voltage division multiple times. Just as a quick aside, how many of you guys remember implementing circuits like this? So like here was 5 volts, here's some resistor, probably a 10K resistor. This guy right here might have been a thermistor or something like that. And then this was connected to some analog pin on your Arduino. Does this look vaguely familiar?
Yes, sir.
This is what's called a voltage divider circuit, okay, where you're literally just using the principle of voltage division to be able to very quickly figure out what voltage is on that analog pin and all of that kind of good stuff. We're going to get into the nitty gritty of how this works here in this class meeting. Okay. So let's consider a series connected network of resistors. And this works for any number of resistors in series. So I'm going to do something very similar to what I did the other day. And I'm just going to connect N resistors in series. And I'm going to define the voltage drop across each of these resistors. So resistor R1 has a voltage drop of V1. R2 will have a voltage drop of V2 like so. And Rn will have a voltage drop of Vn like so. In order for us to apply voltage division, we need to know what the voltage drop is across this series combination of resistors, right? So in this thing up here, the known voltage drop would have been 5 volts because there's a total potential difference of 5 volts across the 10 kilo ohm resistor in series with whatever resistance the thermistor currently has. Okay. Now we are going to make an assumption here, but it's not really much of an assumption. There is going to be some current I that's flowing through this series combination of resistances. If our voltage drop V known is anything other than 0, we know that there's a current flowing through from Ohm's law. So, like I said, not really an assumption. So let's throw some math at this really quickly, okay? And this is going to look incredibly similar to the derivation for how we can combine resistors in series for the first couple of steps. So if we apply Kirchhoff's voltage law, we're going to wind up seeing that V known is the sum of V1 plus V2 all the way out to V sub n. And we know that we can express all of those voltage drops in terms of that current I. So that's going to wind up looking like I times R1 plus R2 all the way out to R sub n, like so. And we could rearrange and say then that I is nothing more than our known voltage drop divided by the sum of all of those resistors in series. I'd be willing to bet that you guys have come up with a relationship incredibly similar to this multiple times when working on your homeworks to this point. So it shouldn't be anything too wild or crazy to comprehend. Now, the voltage V1, according to Ohm's law, is just I times R1. So if we substitute in our relationship for I, that becomes our known voltage multiplied by the resistor R1 will be in the numerator, and then the sum of all of those resistors in series is in the denominator. So effectively, we can say that the voltage drop V1 is just our known voltage times a proportionality constant, right? So and the proportionality constant is just the resistance that we're interested in divided by the total resistance. If we wanted to find the voltage drop across resistor R2, we could do the exact same thing. So I times R2 comes out to be V known multiplied by R2 divided by R1 plus R2 plus all the way out to R sub n. And in general, the voltage drop across the kth resistor is just the known voltage times the resistor R sub k, which is just the resistor we're interested in, divided by R1 plus R2 all the way out to Rn. And we could write this as the known voltage times Rk divided by Req, which is just the equivalent resistance of that series connected network. So let's look at a couple of the nuances of how this relationship is applied. Okay. So let's say that I have a 10-volt source, and here I have 5-ohm resistor, a 2-ohm resistor, and a 3-ohm resistor. And I'm going to define a voltage V3 as, sorry, I should make that V2, that's confusing. Positive polarity on top like so. And I'm going to define a voltage V3 as positive polarity on the left, negative polarity on the right. So I would like for you guys to tell me how to apply the voltage division equation from above to solve for the voltages V2 and V3. So let's start with something easy. What's our known voltage?
10 volts.
10 volts.
10 volts, absolutely right. So if we're solving for V2, what's the resistor that we're trying to find the voltage drop over?
2
2
ohms.
ohms.
All right, so that's the one that's going to go in the numerator. What's the total equivalent resistance? Well, that's just
10.
5 ohms plus 2 ohms plus 3 ohms, exactly right, 10 ohms. So 10 times 2 over 10 looks like 2 volts. Nothing particularly difficult about that. Let's look at V3. So tell me what my equation should look like now that we've got a little bit of practice.
10 volts times 3 ohms over 10 ohms equals 3 volts.
All right, so I agree with everything that you have there. However, there is a little subtle thing that we need to pay attention to. Okay. So when we defined our voltage division relationship, all of our resistors had the same polarity. And by that, I mean the current I that's flowing through them is hitting the positive polarity terminal first for each and every one of them. If our current I is leaving the positive polarity terminal of our known voltage source, Does that current hit the positive polarity terminal or the negative polarity terminal of V2 first?
It's the positive.
What about for V3?
It's the negative.
So what do you think we're going to need to do to correct our voltage division relationship for V3?
-3 volts.
Exactly right. So just like with Ohm's law, if the current hits the negative polarity terminal first, we put a negative sign. So this is simple application of voltage division, okay? We can adapt voltage division to work for more complicated circuits, okay? So let's look at something a little bit more complicated. And I'd be willing to bet that you've had problems like this in the last couple of homework sets. So let's say that we have an 8-volt source, a 5-ohm resistor, a 3-ohm resistor, and a 6-ohm resistor, like so. And we're interested in finding the voltage drop across, we could call that the voltage drop across the 3-ohm resistor or the voltage drop across the 6-ohm resistor. Like I said, you guys have probably seen things like this a couple of times at this point. So previously, you probably would have done something like, well, I could combine a 3-ohm resistor and the 6-ohm resistor in parallel. And then I could find the current flowing around the whole network. And then I could use that current multiplied by the equivalent resistance to find that voltage V. There's nothing wrong with that. It's just a whole lot of steps. Instead, we could apply voltage division to this network. Okay, so let's call this Vx. So to me, we could say that Vx is, so our known voltage is 8 volts. The voltage that the resistance that we're trying to find the voltage drop over is the parallel combination of 3 and 6. So that would look like 3 ohms times 6 ohms over 3 ohms plus 6 ohms divided by 5 ohms plus 3 ohms times 6 ohms over 3 ohms plus 6 ohms. So let's see, 18 over 9, so that's like 2. So 8 times 2 over 7 is 16/7 of a volt, if my mental math is correct. Process is right. My ability to do simple math in my head may not be. So effectively, as long as we can make things look like a series combination of resistances, we can apply voltage division for that as well. We only have 25 minutes left of class, so I don't know that we have time to work this particular problem out, but I want to bring to your attention, let me go back here. Homework set number 3, problem 4. Let me pull it up on WebWork on this computer so that you guys can see it. So this problem, you could work using the methods that we had determined previously. So find the equivalent resistance, all of that kind of good stuff. But it would actually be significantly easier to do if you use the principles of voltage division. So finding the equivalent resistance of everything to the right of the dashed line that says REQ, you could then apply voltage division just like I talked about a moment ago to solve for the voltage V1. But then you could do that exact same thing to solve for the voltage V2, and you could do effectively the exact same thing to find the voltage drop across element R4, and then just divide that voltage by R4 to get the current I4. So applying voltage division to this complicated looking system correctly, and I think this would be very good practice for using it correctly, actually saves you a ton of boring, tedious analysis steps. So voltage division is a very, very powerful tool once you learn how to use it. Okay. All right. So before we move along to current division, anybody have any questions on voltage division? Okay. So our last topic for today is current division, and it is very similar to voltage division, except that it's used to find currents in parallel networks of resistances. Okay. So let's say that we have a network containing multiple resistors in parallel. So let's call this R1. R2. All the way out to some resistance R sub n, like so. Let's say that we have a known current entering this network containing multiple resistances in parallel. There's going to be a common voltage of V over all of these resistors because they're connected in parallel. And I'm going to define the individual resistor currents like so. So the system that I've described is we have a current I known that's flowing in, and then it splits up into I1, I2, all the way out to I sub n. Okay? So if we were to apply Kirchhoff's current law, we could see very easily that the current I known is just the sum of I1 plus I2 all the way out to I sub n. We could express all of those currents in terms of our voltage V. So that's going to look like V times 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. And algebraically rearranging, we could say that V is equal to our known current divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Sorry, that shouldn't be V1, that should just be V. So our current I1 is, by definition, V divided by R1, or we could express this slightly differently as V multiplied by a factor of 1 over R1. And so if we substitute in our relationship for V, this looks like I known times 1 over R1 divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Okay. Our current I2 would be V over R2 or I known times a factor of 1 over R2 divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Okay. And in general, the current flowing through the kth resistor is simply the known current multiplied by 1 over the resistor that we're interested in divided by the sum of the reciprocals of all of the resistors that are in parallel. Or our known current times the equivalent resistance of everything in parallel divided by the resistance we're interested in. For what it's worth, this is the form that I use. The one on the right is technically correct, but I prefer this form over here in the middle because it looks the most like voltage division. The only difference is instead of using the resistor values directly, we're using the reciprocals of the resistor values. So let's, I'm sorry, what was that?
Their conductance.
Effectively, yes. That is a perfect way of thinking about it. So we're using the conductances. So current division for conductances is literally the exact same thing as voltage division for resistances. Absolutely right. I don't typically think in terms of conductance, but that is a very, very good and astute observation. All right, so let's apply this, and then we'll look at a couple of more little complicated type things as well. So let's do a simple application first. Let's say that we have a 3 amp current source. Here we have a 4 ohm resistor and a 2 ohm resistor. And let's call this current I1. And let's call, sorry, I'm going to make that I4 in a second. This one I2. Just so that we're, okay. So how would we apply our current division relationship to solve for the current I4? So what's our known current?
3 amps.
All right. What's the current that we're trying to find, or excuse me, what's the resistor that we're trying to find the current through?
4 ohm.
So we're going to do 1 over 4 ohms in the numerator. And then in the denominator, we're going to have 1 over 4 ohms plus 1 over 2 ohms. So I have 1/4 over 1/4 plus a half. So that looks like 1/4 over 3/4, or 1/3 times 3 amps is equal to 1 amp. Tell me what my equation for I2 should look like, please.
Be the 3 amps
So got my 3 amps for my known current.
multiplied by the reciprocal of the 2, so 1 over 2 ohms
Okay, absolutely.
over
Right.
1 over 4 plus 1 over 2.
So I agree with everything you said, but another thing, much like we had for voltage division, up here, we said that our known current was flowing in, and then all of our resistor currents were flowing out of that node. Well, now our current I2 is flowing in. So what do you think we should do here?
I'll have to flip the sign again, so negative again.
Exactly right. So when the current is flowing in the opposite direction that we would expect, we just flip the sign. So this is going to be negative 2 amps. Okay. So simple application of current division, nothing particularly wild or crazy there. Now let's look at something a smidge more complicated that looks incredibly similar to something that's going to pop up in the in-class assignment here in just a moment. So let's say that I have a 5 amp current source connected in series to a 3 ohm resistance. Let's put a 10 ohm resistor here. Let's put a 6 ohm resistor here and 12 ohm resistor here. And I'm interested in finding this current, which I'm going to call IX. Okay. So this looks appreciably different than the network that we derived our current division relationship for. But I believe that we can still apply current division. Okay. So I know that this may sound odd because current division is defined as, finding out how much resistance splits off when you have a parallel combination of resistances. And there isn't a single resistance that's connected in parallel in this network as it's drawn, but we can combine things to make resistors look like they're in parallel. Okay. So I'm going to give you guys the relationship that I would use, and then I'm going to kind of explain how I did it and then answer any questions that you may have. So I would say that my current IX is 5 amps, which is my known current. And then the branch that I'm trying to find the current through contains a 6 ohm resistor in series with a 12 ohm resistor. And that branch is in parallel with the 10 ohm branch. So I'm going to have 1 over 10 ohms plus 1 over 6 ohms plus 12 ohms. I don't think I can do this math in my head, so I'm going to throw it in the calculator really quickly. So 1 over 18, 1 over 10, plus 1 over 18 comes out to be 25/14 of an amp, or 1.786 amperes. So what I've done here is I've treated these two resistors in series as a single resistance that is in parallel with the 10 ohm resistor, which is what's allowing me to use current division. Now I will entertain questions, and there's one that I'm expecting.
Why do you ignore the 3 ohms?
That is the exact question that I am expecting. Thank you, Ian. So why can we ignore the 3 ohm resistor? So let me erase this red blob here really quickly, right? So I'm considering my known current to be this current right here that's entering this parallel combination of resistors, okay? So I'm ignoring the 3 ohm resistor in essence because all 5 amps flows through the 3 ohms. It doesn't have an opportunity to split. So it shouldn't show up in our equation that tells us how the current splits. Does that make sense?
Yes, it does. Thank you.
No problem. So this is how we can apply current division to something that maybe doesn't look like it should be able to apply. But once again, as long as we can get a network where we have parallel resistances and we know the amount of current that's flowing into that parallel combination, current division is fair game. Any other questions about current division before we start working on the in-class assignment? And I say start because we only have 20 minutes left of class, or excuse me, 10 minutes left of class. All right, so let's look at this ICA. I'm going to go through things kind of rapidly here. I'm okay if we run a little bit long as you guys are. If you need to drop off early, that's perfectly reasonable to me. All right, so we have this circuit here, and our ultimate goal is to find the voltage Vx. So on the left-hand side, we have a network where we have several things that are in parallel, including 3 current sources. And on the right-hand side, we have kind of a smaller sub-network that's defining this voltage Vy. And this voltage Vy is what's controlling this current source over here. So I think that our first step should be to determine what the voltage Vy is. Does anybody have any idea how we might do that?
Ohm's law?
Ohm's law, absolutely right. So go ahead and tell me what that's going to look like.
You'll set Vy equal to -2 milliamps and 1 kilo ohm.
So -2 milliamps times 1 kilo ohm. So that's going to look like -2 volts. Are you sure about the sign there?
The current is flowing into the positive terminal.
You're
It appears to
absolutely-
be, so
Yep,
so it
you're
should just
absolutely-
make
Yep, you're absolutely correct. I was just trying to trip you up. Great job. 100% right. The answer should be -2 volts. Okay. So now that we know what Vy is, let's figure out what that 0.03 times Vy is going to be. So we have a voltage controlled current source. So what are the units on that 0.03? We did this earlier, and it should also be in your notes from our second class meeting.
So do you want the units?
Yes, please.
Amps per volt.
Amps per volt. Thank you so much. So 0.03 amps per volt times Vy is going to look like 0.03 amps per volt times -2 volts. I believe that comes out to be -60 milliamps, or -0.6 amps. Everybody okay with that?
Good.
So what I'm going to do is I'm going to erase this stuff right here, and I'm going to call this 60 milliamps, and I'm also going to put direction down just to get rid of that negative sign. So now I have 3 current sources in parallel, right? So I can effectively redraw this circuit, or at least the left-hand portion of the circuit, as a current source, direction up or down. We'll sort that out in a moment. Here's a 10 kilo ohm resistor. Here's the voltage Vx. So completely arbitrary question. Do we want to make our equivalent current source direction up or direction down? You guys just pick one randomly. Up, okay? So what should my equivalent current look like? Or what should its value be? So I have 12 up, 60 down, and 3.5 down. So that's going to look like 12 minus 60 minus 3.5. Or negative 51.5 milliamps. Looking at this circuit, what should Vx be?
Do the negative 51.5 milliamps times 10 kilo ohm.
Negative 51.5 milliamps times 10 kiloohms comes out to be negative 515 volts. Absolutely right. Thank you, Baylor. Any questions, comments, or concerns before we move along to problem 2?
Is that negative 51.5 because we chose the upward direction?
That is exactly correct. If we had chosen downward, it would be positive 51.5, but the current would be flowing into the negative polarity terminal, and so our voltage Vx would still be negative 515. Any other questions? All right, let's look at problem 2. So we have this large ugly circuit. Once again, we have kind of a sub-circuit on the left and a sub-circuit on the right. Over here on the right is where the voltage Vx is defined, and that voltage is going to wind up getting plugged into what we have over here on the left. So it looks like we need to solve for what's going on the right-hand side of the circuit first, which means we need to solve for the voltage Vx. So does anyone have any thoughts?
Could start by finding how the current is the 5 milliamps is split between the two paths it could take.
Absolutely right, Baylor. So we can apply current division to figure out how much current is flowing, excuse me, flowing through this branch. So I'm going to call that Ix. Baylor, would you mind helping me out and telling me what you think the equation should look like?
Ix equals 5 milliamps be times that. So can we combine that and do 1/10?
Absolutely. So
Ohms in the numerator.
Ohms, okay.
And then 1/10 ohms plus 1/2 ohms in the denominator. Or
Absolutely.
kilo ohms. Yeah.
And let's throw that into the calculator really quick. Actually, let's see. So that's 1/10 over 6/10. So 1/6 times 5 is 5/6 of milliamp, if my mental math is correct. So what should Vx be?
The Ix times 3 kilo ohm.
Absolutely right. So that would be, let's see, 15 over 6 is 2.5 volts. Okay. So if Vx is 2.5 volts, then what is 0.5 Vx?
0.25 volts.
1.25 volts. Okay. So we are asked to determine the power absorbed by the 47 kilo ohm resistor. So to me, that means we're going to need to know either the current flowing through the 47 kilo ohm resistor. So I'm going to call this IY, or the voltage drop across the 47 kilo ohm resistor, which I'm going to call VY. How do you think we could solve for either of those quantities? And this is addressed to everybody, not just Baylor.
The IY.
So we could solve for IY, and I'm not saying it's a bad idea at all. However, I believe pretty strongly that we could solve for VY directly just by using voltage division. So effectively, we could get VY in one step, whereas to get IY, we would have to find the equivalent resistance of all three of those resistors as one step, and then divide, or excuse me, 1.25 volts divided by that equivalent resistance to get IY. So it's a one-step versus two-step thing. It's not a huge difference, but because we just learned voltage division, I would like to apply that one for this particular problem. So nothing remotely wrong with your instinct. I'm just being a jerk and saying, let's do voltage division instead. So I would say that VY is 1.25 volts. The resistor that I'm trying to find the voltage drop over is the 47 kilo ohm resistor. And my network contains 47 kilo ohms in series with 100 in parallel with 20. So 100 kilo ohms times 20 kilo ohms over 100 kilo ohms plus 20 kilo ohms. If I throw this into my calculator, I got 0.92277, so let's call it 0.923 volts. How do I find the power absorbed by a resistor when I know the voltage drop across the resistor?
Voltage squared divided by the resistance.
Absolutely right. Thank you for that, Baylor. So that's V squared over 47 kilo ohms, which comes out to be 18.117 microwatts. Anyone have any questions, comments, or concerns with regards to this problem? Give me just a moment to say hi to my wife and let her know I'm still teaching class. All right, sorry about that. So any questions before we move on to the last problem?
Real quick, could you just go over a quick conceptual explanation as to why you're only dealing with the 47 kilo ohm, the 100 kilo ohm, and the 20 kilo ohm for solving for power or doing voltage division?
Sure. So okay, this is going to take a minute or two, but hopefully it'll make sense. So we know that we have 5 milliamps flowing in here, right? And we found IX to be 5/6 of a milliamp flowing through this path, which means the current flowing over here, either using current division or Kirchhoff's current law, is going to come out to be, let's see, so 30/6 minus 5/6 is 25/6 of a milliamp. Does that make sense, Ian?
Yes.
Okay. So if we look at the current here, we know that this bit is 5 milliamps. And if we look at the current here, that's going to be 5/6 plus 25/6, which is also 5 milliamps. So how much current is flowing through this short circuit to the left-hand side of the circuit?
I'm guessing 0.
You shouldn't have to guess 0. Kirchhoff's current law tells you it will be 0, right? So if I have 5 milliamps flowing in, has to be equal to 5 milliamps plus that unknown current. So the unknown current has to be 0. So effectively, the left-hand side of the circuit and the right-hand side of the circuit are electrically isolated from each other because we know there's no voltage drop across that short circuit, and we just figured out there's no current flowing through that short circuit. So this little short right here doesn't really play any role in it whatsoever. It's just letting us know, treat this whole thing together as one large circuit.
Thank you. That clarifies it up a lot.
No problem. Any other questions before we move on? I get asked that question very regularly. So you're asking a good question that's repeated often. All right, let's look at problem 3. Okay. So we have a similar situation. The circuit shown below is a small signal model for a MOSFET amplifier. If Vs is equal to 3 times sine of 10t volts and Gm is 4 millisiemens, we're asked to determine V out. Okay. So this voltage right here, V pi, controls this current source. So we're going to try to figure out what V pi is. Effectively, we're going to analyze the left-hand side of the circuit, then figure out what's going on the right-hand side of the circuit. So how might we go about solving for the voltage V pi?
Can we do current division to find Ix, and then
So I don't see an IX anywhere, so I'm not.
well, to solve for V pi, sorry.
I was gonna say use voltage division.
Yeah, so voltage division would make sense here because we have a voltage source with a known value connected to 2 resistors in series. So I think voltage division is appropriate here. So that's going to look like 3 sine 10t volts multiplied by 15 kiloohms over 15 kiloohms plus 300 ohms. You want me to throw that in my calculator really quick? So 3 times 15 over 15.3 looks like 2.941 and some change sine 10t volts. Because we're dealing only with resistors, the sine 10t bit is just going to get carried through the entire way. Okay. So now that we have the voltage V pi, let's solve for Gm V pi. Okay. So GM is 4 millisiemens. So just so that we're paying attention, a millisiemen is a Siemen times 10 to the minus 3. So 4 times 10 to the minus 3. And if we recall, a Siemen is the reciprocal of an ohm. So it is an amp per volt. And I'm going to multiply this by V pi of 2.941 times the sine of 10t volts. So multiply my previous answer times 4 times 10 to the minus, 10 to the minus 3. And I get 11.765 sine 10t milliamps. Anyone have a problem with what I have done there? All right, so nobody's telling me that they have a problem, so I'll assume you're all okay with me just plugging in those numbers there. So how are we going to find V out? All right, so let me just put some stuff here. So let's just say that we had 11.765 milliamps. We can tack the sine 10t on at the end. So we have a current source in parallel with 2 resistances. And we're trying to find a voltage. What should we do?
Current source times the
I don't know if you were aware that you cut off there, Mr. Utley, but please finish your thought. You're definitely on the right track, I believe.
so the current source times the known resistance over the equivalent.
So it sounds a little bit like you might be trying to apply current division here or some weird combination type thing. So realistically speaking, we could, if we were so inclined, use current division to find the current flowing through this 5 kilo ohm resistor. And then knowing that current and the 5 kilo ohm resistor value, we could find the voltage. However, that's not what I think we should do here. Like, I know this is going to sound weird, but it's the less obvious solution is actually to just use Ohm's law. So if we have a current and we have 2 resistors in parallel, the current times the equivalent resistance gives us the voltage that we're looking for. So we don't need to complicate things with current division in this particular case. It's not actually making things easier. It's adding more steps as opposed to taking them away. So I would go with the route that V out is just going to be, our current GMV pi times the parallel combination of 100 kilo ohms and 5 kilo ohms. So that's going to look like 11.765 sine 10t milliamps times 100 kilo ohms times 5 kilo ohms over 100 kilo ohms plus 5 kilo ohms. So let me do that. 100 times 5 over 105. All of that times 1,000. And I get 56.022 sine 10t volts. Now, notice here, there's a minus sign on the answer provided. Is that minus sign correct?
Yes, sir.
It absolutely is, because the current is flowing into the negative polarity terminal. So I should have put a minus sign out here on front, which would put a minus sign right there. All right, thank you guys for your patience with me and allowing me to run 16 minutes over time. I'm going to try very hard not to be a jackass and forget to upload the video tomorrow morning. So I will get it to you guys as soon as I possibly can. And I just want to remind you that I do still have jury duty on Monday. So I'm going to put a link to a video up just in case I'm not able to make it to class. I will probably put an announcement up on Canvas when I have a better idea of how long that's going to take me. Thank you guys for your attention and your participation. And I will see you all on hopefully Monday, but definitely Wednesday of next week. If you have any questions about anything, please don't hesitate to shoot me an email over the weekend. Thank you again.
Thank you, Dr. Hartman.
You're very welcome.